First, thanks the organizer for giving me the opportunity to give this talk here. I'm going to tell you about the so-called Tkachenko mode, and this is a work done in collaboration with Etienne Du, Sergei Moroz, and Dung Nguyen. Etienne is here, and Etienne has a poster about another work that we have done that may fit better with the talk that we have heard today. But I'm going to tell you a story about the Tkachenko mode. First, I want to explain what is the Tkachenko mode, what is it from the symmetry point of view, and then construct series of theories. The first theory is very simple, a linear theory of the Tkachenko mode, and then go to the nonlinear theory, and we will see why the quite exotic formalism of non-commutative field theory is useful for this problem. And at the end, we are going to make a prediction or obtain a new result on the decay rate of the Tkachenko mode. So let's take a two-dimensional Bose-Einstein condensate and rotate it. Actually, that has been done in cold atom experiment. We know that we rotate a superfluid. A superfluid cannot accommodate a rigid motion. What happens is that there will be a lattice. It will the rotation will be accommodated by quantized vortices around each of the vortex. The circulation of the fluid is quantized, and depending on how fast you want the superfluid to rotate, the density of the vortices may be large or small. The faster you want to rotate you rotate the superfluid, the denser the vortices are. Okay, so let's imagine the following situation. That's actually one of the nice things one can imagine doing in a cold atom experiment. Naturally, in a cold atom experiment, one usually put a system in a harmonic potential, and the harmonic potential has properties that it will counteract the centrifugal force. If you go to the rotating frame, for example, then each of these atoms will be subjected to several forces. The first force is the centrifugal force. If you don't have the trapping potential, then the whole system will fly apart. So now imagine that you put a system in a harmonic potential with a frequency fine-tuned so that it exactly cancels out the centrifugal force. And then you would have a system where on each of these particles, the only interaction that it is subject to is the Coriolis force plus the forces from interaction with other particles. So now the problem clearly is equivalent to the problem of a system of boson in a magnetic field, where the role of the Lorentz force is now played by the Coriolis force. And one can write down the formulas and convince oneself that effectively we have a magnetic field whose value is proportional to the rotating frequency. So here we realize a system that is basically a superfluid or in a magnetic field. And the magnetic field, the way that magnetic field penetrates the superfluid is that it creates these vortices. Okay, so the Tkachenko mode is the elastic waves that propagate on this lattice of vortices. Like in the solid, solid is a lattice of atoms. Here we have a lattice of vortices, and so we should expect modes that correspond to the fluctuation of the position of the vortex of the vortices. The problem of the elastic waves was first considered by Vladimir Tkachenko around 1965 to 1969. And then the theory is developed further by many people. It was observed has been observed in BEC of ultra-cold atoms It has been also conjectured to play certain role in the physics of compact stars, where the core of the star can be a superfluid, and if the star rotates, then we would have a superfluid vortex, and there might be modes correspond to these waves propagating inside the star. So there is a nice review by Sonin that I recommend people to look at to see the big picture of where the Tkachenko mode can be observed. So the most obvious place where the Tkachenko mode would appear would be in the rotating helium-4, but unfortunately it's very difficult to observe the vortices in a superfluid in superfluid helium. Okay, so there are several strange features of the Tkachenko mode that are known. First of all, it has a quadratic dispersion, omega equal k square at low k. Very different from a sound wave in a solid, although it is, as we said, it is fluctuations of the position of the vortex in the lattice. Omega is equal to k square. And furthermore, it has only one polarization. There is the waves are transverse. There is no longitudinal mode. Another distinction compared to sound wave in solid. And another feature is that it is one Nambu-Goldstone boson shared by several broken symmetries. A lattice breaks two translational symmetry along the x and the y directions. And we also have the breaking of the U1 phase of the condensate. That's because we start our system from superfluid. These three spontaneous breaking broken symmetry share one Nambu-Goldstone boson. That's a feature that was considered and explained first by Watanabe and Murayama. Another interesting thing about this problem is that one can go to the so-called lowest Landau level limit. That is a limit very popular in quantum Hall physics. If we rotate the system with sufficiently high rotational frequency, then one can achieve a regime in which the distance between the Landau level in energies is much larger than the average interaction energy between neighboring particles. So that's how fast you have to rotate the Bose-Einstein condensate to achieve this result depends on what is the interaction between your bosons. But there is a regime where all the bosons are on the lowest Landau level, and one can ask questions that usually one would ask in the fractional quantum Hall physics, like what is the role of the GMP algebra, the role of non-commutativity in spatial coordinate, etc. Except that this problem might be a little bit simpler than the typical fractional quantum Hall problem. First of all, the system here is gapless. So we know that there is this Tkachenko mode. So that has an energy that goes to zero as k goes to zero. It simplifies, turn out to simplify a bit of the discussion later. The filling factor nu for the boson can be larger than 1, and one can go to a regime where this filling factor is much larger than 1. So in this case, each of the orbital is occupied in average by a large occupation number, and the system can be described as in the mean field approximation, where we treat the condensate as the classical field. So this lowest Landau level mean field regime is the regime where one expects the vortices to appear. And that system should suffer a transition to a quantum Hall regime at some value of nu of order 1. The exact value of nu where that happened is not exactly known, but it's of order 1. Okay, so let's look at this problem from a slightly different point of view, using the dual description of a superfluid. We know that 2 + 1 dimension, the Nambu-Goldstone boson is equivalent to a photon. In 2 + 1 dimension, photon has only one polarization. So the vortex lattice in this dual language can be interpreted as the lattice of charged particles interacting through the photons. So that photon is the Nabu-Goldstone of the superfluid. So let's look at this picture. So here we have a lattice of vortices. So these vortices can fluctuate in position. I'm trying to draw the fluctuation here. And these vortices also interact with each other through the exchange of a photon, a mu. So they are charged, and when they move, they create electromagnetic fields and then interact with each other like that. Okay, so turn out that the Tkachenko mode is a mixture of the superfluid photon and the transverse acoustic phonon. And that feature explains the strange dispersion relation of the Tkachenko mode. So let's first try to develop at the very elementary level, almost at the level of Kittel, the quadratic theory of Tkachenko mode. Here, what we have is, in these two terms, just the usual linear theory of a solid. Right? This is elastic energy, kinetic energy. One feature here that turned out to be, at the end, not very important, but for completeness, I wrote down this term, U dot, and that is because the superfluid provides, in the dual description, a uniform magnetic field. The density of the superfluid after dualization becomes the background magnetic field, so I have a U dot term because each of the charged particle, when it moves, it could obtain the Berry phase in the magnetic field. The superfluid itself is described by the Maxwell term, E square minus B square action. The most important part is the coupling between the phonons, the lattice, and the photons. And this U dot E term encodes the following information. If I have a charged particle and I move it away from the equilibrium position, one creates a dipole, and that dipole interacts with the electric field. So it's U dot E. So all terms here are linear, quadratic, and one can just write down the equation of motion, diagonalize it, and then find the modes. And in this way, one can find that the only gapless mode is this mode with quadratic dispersion. Now I'm going to show you how it happens in a slightly simplified way of calculating. Diagonalizing this Lagrangian is possible, but one can also do the following shortcut. We know that at the end, omega is of order q square, and so that is much smaller than q. The fact that it's much smaller than q allows us to drop several terms, two terms in this Lagrangian, u dot square and e square. And the reason is that, for example, e square has one two-time derivative, but b square have two spatial derivatives. A time derivative is penalized compared to spatial derivative in the regime omega much less than q. And so this one has the following properties. This action, if I now differentiate with respect to the gauge field A0, the component zero component of A, I get the condition that the divergence of U is equal to 0. That explains why the Tkachenko mode is only transverse is a transverse wave. The non-transverse wave is the compressional mode actually turn out to cost too much energy due to the interaction with the electric field here. So only the transverse wave survive in the IR, and one can solve this constraint divergence of U equal to 0 by using introducing a scalar field phi and rewrite U as a curl of phi, roughly speaking, and then one can put this U back into the Lagrangian, integrating out AI, and then get the final action, which is the action of a Lipschitz scalar. That is phi dot square minus graph square phi square. So here we see that this theory naturally give us a scalar with a quadratic dispersion relation instead of a linear dispersion relation. But one question one may ask here is that what forbids the appearance of the usual kinetic term, the gradient of phi square? Is that something in the usual way the Lipschitz scalar theory is described? We always have to fine-tune the coefficient of grad phi square to get to this Lipschitz point. Here, everything seems to happen automatically. Why is that so? And the reason is the following. We have a relationship that we have here. U is equal curl of phi. So here I'm going to be a little bit more careful and introduce a length scale here, L square, so that phi is dimensionless. And so this relationship tells us that the spatial translations are dipole symmetry. That is, when I want to translate the lattice by a constant amount, I have to translate phi by a linear function of x. So this symmetry that the lattice has, translational symmetry, imposes the dipole symmetry, and that forbids the gradient of phi square term and leaves us with the Lipschitz scalar field theory. Only with scalar, the spatial derivative always appears as grad square. But now there is a slight problem one can notice. That is, if we are discussing a system in a magnetic field, and in a magnetic field, we know that the two translations do not commute. Translation along the x direction and translation along the y direction commute to the charge times L squared, that is the square of the lattice of the magnetic length. And that is not realized in the current version of the dipole symmetry. This px and py simply shift phi by a linear function of x or linear function of y. We can do px, py in any order and the result would be the same. So in order to properly encode the magnetic translation symmetry, we have to somehow treat the symmetry slightly better in a non-linear way, presumably, and then hopefully we will see how this symmetry is come out. So that is something that I'm going to do now. Okay, in order to do that, we have to try to understand how to encode the information about the lattice in a non-linear way. That is, going beyond the approximation where the displacement of each of the points is treated as a small parameter. So here, the standard way to write down a theory of a solid in the nonlinear level is to think about a state of a solid as a map between two systems of coordinates. One is our usual system of coordinates in space, and the other system of coordinates is the system of coordinates frozen into a solid. So imagine that you have a solid in the ground state. So you draw some system of coordinates in that solid, and then when the solid deforms, you imagine that that system of coordinates deform with the solid. So a state of a solid can be thought of as a map between two systems of coordinates, the external system of coordinates and the internal frozen system of coordinates that I call capital X. And this capital X, if I expand around small x, it will give us the usual displacement. But I don't have to treat this displacement as small number. I can just treat this capital X as something that can deviate by a large amount from small x. So in this description, the density of points on the lattice, in our case, the vortex number, density of vortex number current, has a nice quasi-topological form. That's J mu is equal to this epsilon times derivative of x, derivative of x. And you can see it this way. If I take one of the coordinates, the index mu to be 0, this rho is the Jacobian of the transformation of small x to capital X. And that fits with the picture that the the system of coordinate capital X is frozen in the fluid. So the density is clearly the Jacobian of that transformation. And N0 here is the equilibrium density. Now, if we write down the nonlinear theory, we can write it down. And here I'm showing you some most important terms that we would have. So first of all, we have to couple the gauge field small a mu, this dynamical gauge field a mu, the Nambu-Goldstone dual of the Nambu-Goldstone boson, to the vortex current. So that is this term here, a dx. Since we couple a mu to a conserved current, that term is gauge invariant automatically. And then we have to write down the elastic energy of the solid. And then there would be a term like B square, that is the density, B is the density of superfluid, and so B square would have information about the compressibility of the superfluid. And then there is a background rho naught that we have to put in here, so that the constraint that appears when you differentiate the action with respect to A0 have this form. So let me explain this. This is telling us that the Jacobian of the transformation from one system of coordinates, the external system of coordinates, to the frozen system, is area preserving. That basically is the nonlinear version of the statement that the Tkachenko wave is transverse. So this, if we expand this expression in linear order in the displacement, we get back the information that the wave is transverse. So, but to nonlinear order, the information is the following: that the mapping from X to capital X is area preserving. So we want to parameterize all possible area preserving diffeomorphism of a two-dimensional space. So I'm going to go a little bit further and speculate that at the quantum level, something even more interesting happened. So we know that if we have a physics that happen completely on the lowest Landau level, then the guiding center coordinates X and Y do not commute. It commutes to values that is the square of the magnetic length. Now, the statements that the Jacobian of the transformation from small x to capital X is equal to 1, this one, can be thought of as a semi-classical statement, whose quantum version should look like the commutator of capital X and capital Y is equal to I theta. So imagine that you try to compute the commutator of two functions of small x and small y. So the linear order in H bar, you would get the Poisson bracket, and that is this Jacobian here. So let me speculate that the correct way to impose the incompressibility condition is that the coordinates, the frozen coordinates, also commute to the same value as the space-time coordinates. And that can be imposed if we say that the transformation from small x to capital X is a unitary transformation. So imagine that we have a Hilbert space that we have the Heisenberg algebra that's spanned by X and Y, and this X is some elements in this algebra whose can be represented as a result of a unitary transformation acting on this X. One can check very easily that the commutator of X and Y would not change. X1, capital X1 and capital X2 change. And so here the thing that we see here is the following: that we can identify the Tkachenko mode with a certain operator phi, which is itself is a function of this non-commutative coordinate X that parameterizes this unitary transformation. So the point of view that we gain here is that the Tkachenko mode is a field in a non-commutative space X. A function of non-commutative X that is a field of a non-commutative field. Non-commutative field theory has an origin in high energy physics. The idea of non-commutativity of spatial coordinates is very old, but the non-commutative field theory became popular in relations with some observation in string theory around 1999. And then later on, several people tried to apply non-commutative field theory to fractional quantum Hall effects, in particular Hart and Samtel was trying to build a theory of bosonic quantum holes, a bosonic quantum Hall state using non-commutative field theory. Now, in our case, I think the situation is that we can, this non-commutative field theory can give us an interesting result, at least interesting way to view the Tkachenko mode. In non-commutative field theory, the coordinates do not commute, and so field, when we write down phi1 times phi2, we have to be careful to write whether phi1 is phi1 phi2 or phi2 phi1. One popular way to deal with the non-commutative field theory is to map it to the usual commutative field theory through a very well-defined procedure in which any operator is replaced by the so-called its while symbol. So, for example, operator x would be mapped to just a number x, or the anti-commutator of x and y mapped to x and y, etc. There is a well-defined way to map an operator, any polynomial of x and y, into a polynomial of commuting x and y. And then in this mapping, the product of two operators is replaced by the so-called star or Moyar product of two functions, of two of its while products. So to leading order, it's we have just a dot b, but then when we expand, there is term with involved derivatives. Okay? And there is this series goes to infinity. Okay, so now let me tell you how magnetic translation looks like in this non-commutative field theory. Okay, it turned out that in the magnetic translation mapped to the left multiplication of the, so this phi here is the Tkachenko mode. E to the I phi is that while symbol of the canonical of this unitary transformation from small x to capital X, and the magnetic translation is the multiplication by star product on the left of exponents of a linear function of x. Okay, so if we think about expanding this to leading order, phi prime is simply equal to that c cross x plus phi. So it's just the usual dipole transformation that we have before. But in fact, we have to use star products, and then there is an infinite number of terms that involved in particular terms that have derivative of phi. And now, because of the properties of the star product, the two translation now do not commute. And one can check that the commutator of two of these p along two perpendicular directions is equal to an operator q, which shifts phi to a constant. So we know that this q has to be identified with the U1 particle number, and so that phi clearly transforms like a superfluid phase. So the Tkachenko mode, which is a non-commutative field, is also a non-commutative. In some sense, it's non-commutative Nambu-Goldstone bosons of the superfluid. Okay, so now we can construct the interacting Lagrangian based on the idea of non-commutative field theory, with the constraint that the Lagrangian has to be invariant under magnetic translation. So, and one can develop the whole formalism. So I'm not going to go through here. Instead of writing derivative of phi, one has to be careful and write some kind of improved derivative so that it transforms transformed in certain simpler way under magnetic translation, and one can write down any most general invariant Lagrangian. So the magnetic translation and symmetry put further constraints. So let me tell you what happened at the end. At the end, if we write down the most general Lagrangian and then expand to cubic order, we get several terms. And all these terms contribute to the decay rate of phi goes to 2 phi. One Tkachenko mode decays into 2 at the same order in the dependence of the energy of the initial particle. So the decay rate of the Tkachenko mode is cubic over its energy. So this result, I believe, is new. There was a previous result by 2 authors in 2011, but I believe that result is not correct. Gamma of order E. This result that we obtained tells us that the Tkachenko mode becomes a sharply defined quasi-particles at low energy. Okay, so let me, since I am out of time, skip a few slides and go to the conclusion. So the Tkachenko mode is a sound wave, but with a quadratic dispersion relation, which is a common non-Nambu-Goldstone boson of particle number in magnetic translations. But from the information that the magnetic translation have to be not commuting, we find that this Nambu-Goldstone boson is best viewed as a Nambu-Goldstone boson in a non-commutative field theory. And from the structure of the theory, we can derive the decay rate of the Tkachenko mode. Gamma is equal to E cubed. Thank you very much.
Example of Goldstone mode that doesn't have well-defined quasi-particle at low energy?
I don't have any example. Yeah. So the authors Matveyенko and Shlyapnikov 2011 claim that when the calculation gamma would be of order E, that would tell us that the Goldstone boson, Nambu-Goldstone boson, is not a well-defined mode at low energy, which is very strange. I believe the correct answer is more conventional.
But is there any general principle that forbids that kind
usually
of thing?
In this it's usually each of the Goldstone bosons should appear with a certain number of derivative in the action. So here, for example, the derivative, this term has too many derivatives, so that gamma can be of order E. So the symmetry is I can go case by case, but I don't know any general argument.
Hi. At the beginning of the talk, you said that this Tkachenko mode is like a shared Goldstone mode of like 3 different symmetries breaking. From this non-commutative field theory, do I understand? Like, is there a way to understand that? So
all of these symmetries are realized at the level of a single Goldstone boson. The 2 translations, the translation basically correspond to multiplying e to the I phi by exponents of a linear function of x, and the U1 symmetry by multiplying by exponents of a constant. And so that's the single Goldstone boson realize all 3 broken symmetries.
I see. Okay. Thank you.
Hello. Yeah. So the power law that you obtain for the scaling, for the scattering at the end. So does that depend on the fact that there is a non-commutative structure? For example, I could think about a commutative variant of a Lifshitz Lagrangian, and then so that is my question. Does it depend on the?
No, it doesn't. Actually, if one just forget about the non-commutativity, at this level, cubic level, the usual dipole symmetry would give only these structure. Maybe need to impose one more like PT symmetry to get rid of one possible term with phi dot square. But you get all this. So we are just being careful with the symmetry, but the result come out to be the same as we would get with the naive.
When would the non-commutative structure show up first or most prominently?
It's like in the 5 to the 4. 5 to the 4 terms. Yeah, you would get term. So we haven't analyzed it, to be honest, we haven't analyzed it very carefully, but the fact that all these terms in the non-commutativity can be written in this form that coincide with what would happen, what one get from naive Lipschitz theory requires a bit of integration by parts. There are a lot of terms that don't look like that, but at the end can be brought into this form by integration by parts. And so that might, I guess that this will not continue at the level of 5 to the 4th, but we haven't tried to classify all these terms.
Thank you.
Yeah.
Yeah, maybe I ask a question. So this structure of these nonlinear corrections, given that it descends from this non-commutative field theory, are the coefficients, the relative values constrained to have some particular values? Because it descends from the non-commutative theory.
One can actually identify these terms with certain properties of the whole system. For example, the G3, the G2, for example, would correspond to, would be equal to derivative of the Young modulus over density, over chemical potential, for example. And G3, just G1 would correspond to a term in the thermodynamics of a superfluid without vortex. G3 is a certain nonlinear elasticity coefficient. So all of that have equilibrium interpretation.
But they're independent coefficients.
They are independent coefficients.
But presumably the structure of higher order nonlinearities is just fixed, right? Even the coefficients.
No, they are not fixed, unfortunately. This whole invariant Lagrangian is a function of these variables. And when one expand a function in Taylor series, then each time we get new coefficients. So unless there is the principle to fix the function itself, it's a function of two variables, or more than two. It's this and then a few invariants.
But the expansion of star products will give you a particular nonlinear structure, but then the nonlinear terms, the action itself.
The nonlinear terms come from first. They come from several. So first of all, when you expand, you get this term, but then it's also inherit from term with less value of phi. Yeah. But when you expand it, because then you get this. Yeah.
Thanks. Yeah, I have a couple of, one or maybe two questions, basically related to the relation to superconductivity. If you had a 2D thin superconductor with a very long penetration depth, then normally we think that looks very much like a superfluid. Do you understand how the vortex lattice in that case would reduce to this?
I think it would be exactly if the penetration depth is large.
And when it's large and not infinite, is there what happens beyond that scale?
When large is not infinite, then presumably the prediction omega equal q square has to be revised below that scale. When 1 over q is larger than the penetration depth, I think one should go back to just linear dispersion, because now the Tkachenko mode is just now a pure oscillation of the lattice. There's no mixing with the gauge degree of freedom anymore. So it will go back to the just usual elasticity theory.
Yeah, I think it makes sense. Then a somewhat related question. Would you be able to derive the same Lagrangian starting from just the Abrikosov solution for the vortex lattice, and allowing a phase to vary in that complex function? It seems like you get this kind of dipole symmetry from the linearly varying phase factors.
That's something we would like to do. We haven't been able to do that. Actually, I think that needs to be done in order to settle this discrepancy between these two results, because Matvienko and Shliapnikov, they try to do exactly that. They start with the exact Abrikosov solution and then try to expand. I believe at some point they made a mistake. I can point to some place, some place where I think we should do better, but I haven't been able to do to find out how to do it the correct. Well, it looks complicated.
Okay, thanks.
Yeah.
So is there a way to do a non-commutative field theory without this semi-classical approximation to the Moyal product?
From the point of view of effective field theory, we always have we always can limit ourselves to the first term, because in the Moyal product, because the term that follows it has more derivatives, and so at low energy, typically these are suppressed. I'm not sure if one can go if it makes sense to go beyond this this first term. Could be that because the Moyal product encodes exactly the symmetry of the theory. Maybe there is, in some sense, there is a way the theory knows about this dot term. Let me show you one thing, one slide. That is one can derive from this theory the exact GMP algebra. This GMP algebra, if we write the theory with exact Moyal, this star product, we can convince ourselves by general argument that the density that comes out from this theory commute in a way that it's GMP. That's exactly the GMP algebra.
Okay, thanks.
I think, any further questions? No? Not, then we thank Sohn.
Thank you.